the Rosetta calibration plugin, which is a fresh plugin that you can find in Flojo Exchange. So let me first share my screen here. Okay. There we go. Okay. So we're going to be talking about the Rosetta calibration plugin that will basically allow us to define the size range of extracellular vesicles with flow cytometry or any other particles that we're interested in run with our cytometer. My name is Ioannis Panetas. I'm a European application scientist at Flojo and BD. If you have any questions throughout the webinar, please feel free to type them in the chat box, and I'll make sure to address those. Yeah, so so we're going to start this webinar with a bit of a background and an introduction and background of the plugin and when it makes sense for you to use that plugin. And then I'm going to show you how to install the plugin. So it needs two separate installation of the plugin and also another software, which is the Rosetta calibration software developed by the Xometry company that will be needed in order to run this plugin. And then we're gonna see how it all works out in Flojo. So, we'll be hearing a lot about extracellular vesicles. So extracellular vesicles are a generic term for particles that are naturally released from the cell. And they are delimited by a lipid biolayer. And they have a subcellular size and are present in fluids and have a continuous cell interaction. So they communicate with cells, and that's why they're currently under the microscope in many different fields. And as we're going to be seeing also later under the flow cytometer, of course. So, and because of their various applications, they're under intensive research. So some of the application include liquid biopsy biomarkers, therapeutic agents, quality monitoring of ecosystem, food production, and many more. However, one of the most challenging factors in EV research is data reporting. Yeah, it always has to do with data, and more specifically, with their characterization due to their subcellular size. So there has been till today many different protocols developed and methodologies for their characterization, like nanoparticle tracking analysis, electron microscopy, and as we're going to be talking about today, also flow cytometry. So what will happen when we run an extracellular vesicle sample in a flow cytometer? Let's say we have a urine sample or any kind of sample that contains EV extracellular vesicles. Yeah. So if we take, for example, here on this plot, a urine sample, and say we need to determine the size of the particles within, that would not be possible. So from the scatter plot here, the side scatter and the forward scatter in that case are defined in arbitrary units in the flow cytometer. So what that means is that we cannot just simply draw a gate here and based on the forwards and side scatter to separate into different sizes, because this would be a non-standardized measurements, and we cannot know if the particles are in the expected size range. And the same applies when we run the same sample into a different cytometer. So speaking of different cytometers, a second concern is having to do with those different cytometers that we can run the same sample, and the variability in reports. So using cytometers with different limits of detection will generate different reports concerning the diameter of the particles that were detected, as well as the concentration. You can see that here on the figure, where 3 different cytometers and 3 different limits of detection in that case will generate different reports. So in the third cytometer, we would have EVs more than 600 nanometers. In the second cytometer, more than 300 nanometers, and the first cytometer above 100. Yeah? Therefore, there is a need to somehow calibrate those different cytometers and have a standardized measurement of the size in order to have accurate reports concerning the size of EVs. So what exactly calibration will do in that case? Yeah, so on the plots again on the right, you can see the same sample run on different cytometers. Yeah, so you can see side scatter versus anti-GFP in that case. We're having exactly the same gate on the same sample give us a different result. So, so in that case, we cannot use the side scatter height in order to compare when we have uncalibrated data. So with calibration, we basically want to convert those non-standardized measurements into standard units of measurement. So that way we have the same results concerning the diameter of particles. So this we can see here. So after calibration, ideally, we want to transform the side scatter height or using any scatter channel in that case, and want to have as an output the diameter. So now those samples here are comparable, and now we can place the same gate, even though we have different instruments. And as soon as we calibrate, we can now, even if the instruments have different optical configuration, we can convert those into this standardized measurement. And that's what we're going to do with the Rosetta calibration software. Okay, so there are different kinds of calibration, so you can use different kinds of beads for calibration. The kind of calibration that we're talking today concerns calibration through the light scatter. Yeah, so the light scattering can be used to for the size or diameter calibration. So depending on how well the particles that we study scatter light, something that is termed as refractive index, different particles with the same size can have different scattering intensities. So let's take another example here. Here we see that EVs, extracellular vesicles, have a refractive index of approximately 1.4 and scatter less light than the same size of polystyrene beads. Yeah? So, and those differences are because of the refractive index, where EVs have 1.4, silica beads have 1.45, and polystyrene beads 1.61. The scattering intensity also depends once again on the cytometer. So it depends on the collection angles, the wavelength and illumination, and so forth. So we can now use beads of a known diameter, which are in that case, in this plot below. We can use, for example, polystyrene beads and of a known diameter and refractive index. So those black data points here are basically the measured sizes of polystyrene beads, and those will have a relative light scatter intensity. Okay, so now we have something known here, and through the me theory, so through a complex mathematical equation, we can draw this line and collect those data points. And now we can correlate the intensity with the diameter. For example, we can see here that when we have 100 nanometer polystyrene beads, we get an intensity of 10 to the power of 4. And that would correspond with our EVs and their specific refractive index to a diameter of approximately 200 to 300 nanometers. So this theory and having beads, known bead size and refractive index, and as well as known optical configuration settings for our instrument can help us then approximate the size of and the diameter of the particles within our samples. And that's exactly how we're gonna calibrate using the Rosetta calibration software. Okay, just gonna check if you have any questions here. Okay. So, of course, all those calculations might seem a bit difficult and complicated. So that's why we equipped with the Rosetta calibration software. So this is developed by the Exometry company, which you can access through the website exometry.com. So there you can perform this calibration using light scattering signals, and then we can convert into nanometers using the software there. So basically their product consists of polystyrene beads. So we have standardized beads with specific diameter, different diameters, and a known refractive index. Okay, so together with the beads, you also get the Rosetta calibration software, which will determine then the scatter to diameter relationship automatically. Okay. So the software will add a new channel on your FCS file, which will be diameter in nanometers. Okay. And as we're going to see later, we can connect this platform and this software in Flojo, and then we can gauge on the different sizes of particles within the sample. So this software will simplify the calculations using the me theory, so you don't have to be bothered with all the math behind it. And the software supports a number of different cytometers that you can use for the calibration, and you can adjust the calculation for each different cytometer you're collecting your sample, and also you can adjust the refractive index of different particles that you might be studying. So the principle for size detection using this software is the following. So basically we would need, of course, to have acquired an FCS file with the Rosetta calibration beads. And after we collect the beads, we can end our samples. that is supported by the software, we can then execute the platform on the controlled bit FCS sample. And what we're going to be getting in that case is FCS file that we loaded on the software, and we have measurements, which here you see the data points of a known diameter beads and the relationship with the light scatter intensities. Yeah, so this is what we have known. And then the software will calculate and connect those data points, as we said before, through the me theory, and draw those lines for the polystyrene beads. And depending on our sample of interest, if it's EVs or any other particle, we can input the refractive index and characteristics in order to calculate the relationship between intensity and diameter of the particles. And then the derived parameter can be brought back to the samples as a new parameter that we can use to get. So all those calculations and access to the software is also connected with FlowJo using the Rosetta calibration plugin. So basically the methodology here is the following. We will first traditionally add and import our FCS files, including the beads and the samples in a FlowJo workspace. And then we're going to begin by running the plugin on the bead control. Yeah. So then this will direct you to the Rosetta calibration software, where you can visualize the data points and perform the different kinds of calculation. And finally, you can input in the middle section here, you can input the refractive index of the material you study, the model type and medium and so forth. And last step, you can press the return to FlowJo button, where then the diameter parameter will be derived to your FCS files. And then you can use this for getting different sizes of EVs and understanding more the phenotypes of different EV sizes. So that's the overview of the plugin. It basically, what it does is to connect FlowJo with the exometry Rosetta calibration software. Okay, so that's it with the background here. So I will now quit the presentation, and I just want to show you step by step how we can, how you can find everything. Okay, so I will open here. I will open here the website first, because as I said before, we need two different installations. Okay, so first I go to the exometry website. So that's the exometry website here, where you can find here information or news. So the latest news is the release of the plugin here. And you can find the products here on the top tab here. And what we're talking about today is the Rosetta calibration. Yeah. So if you need more information or how to run it on your cytometer, why to use the Rosetta calibration, if you want to order the beads to run. So basically you would need to have those beads purchased, and then you can use this software with, you know, having acquired the sample, and you also get access then to the software. There are very interesting manuals here, step by step, how you can calculate the diameter of EVs. And in addition, you can find the different cytometers that are supported here. Yeah, so the software has the configuration of all those cytometers that you can use to identify the size of extracellular vesicles. Okay, so very first step, we go to downloads, and then we need to download the software. Yeah, you can download for Windows or for Macintosh here, and it's just a simple installation. You install it, and then you have a new app, a new program on your system, which is the Rosetta calibration software. So that's the first step. So you can do that first. And the second step is to go at the Flojo Exchange website. So that's the Flojo Exchange. And here you can find all of our different plugins. Yeah, so there is a list with all the different plugins. And since it was recently installed, it's right at the bottom, you will find Rosetta calibration software plugin. So I can select here, and you get a description of the plugin, what we discussed already, and you can download here. So I can hit the download button, and this will create a new zip file downloaded. So you can feel free to drag and drop it in the desktop or anywhere you like, and then unzip that file. Yeah, so we need to unzip. And that applies for most of the plugins we have there. So you would need to download, then unzip the file. And within the file, for each one of our plugins, we have two files within. The jar file, which is basically the plugin itself, and you have a PDF document. So the PDF document is a manual on how to install and use the plugin. So if I open here just to show you, so we get the description of the plugin in this document. It's really the manual and has all the information step by step. Plugin installation, so the plugin does not use R, so it doesn't have any dependencies or R, and you don't need R in order to run it. How to use it, you select your control, you run the plugin, and then the very first time that you run the plugin, you would need to input the location of the Rosetta calibration software. So you need to select the executable file and then press open. And then this you only need to perform once, and then you can keep using it without every time selecting that folder. Yeah, and all the rest of the steps we're gonna see later on when we open Flojo. Okay, so that's the manual within the folder, and then the jar file here, which is the plugin, you can copy that. Okay, and then you can paste that into your plugin folder that you have. So by definition, when you install Flojo on your computer, you will be getting a plugin folder. Yeah, so here I have my plugin folder where I have all those jar files. So I only need to paste that jar file here, and then I'll show you how to direct Flojo into this folder. So this is typically for Mac. This folder is located under applications and plugins. So it's here for me. And for Windows, this would be in the program files, Flojo, and plugins. Okay, so you only need to transfer the jar file here. Going next, going next, we can we can open Flojo. So I'll open the Flojo app here. So the latest version is the 10.8.2 for Mac, and I will sign in. Okay, so that's the Flojo workspace here. To finish with the installation steps, you need now to find the root and select the location of the plugin folder. So this you can do by selecting the preferences button here, and under the preferences you can go to diagnostics. Yeah, preferences diagnostics. And now you can select at the bottom, you see the scan for plugin option. Here you can select where this folder is located, so you can choose. So here for me, this folder is application plugins. Yeah, so if you have any other location of your plugins, just input here the folder, and then after you restart Flojo, it should be all the plugins should be available to you. Okay, so I have here some FCS files that we can use. So I have some demo files from Oxometry, and I'll just import this folder into Flojo. Okay. So we have here the two samples. So we have the Rosetta calibration beads that we ran, and we have an extracellular vesicle sample. So if I open one of those, so if I open my sample, I will see side scatter and forward scatter are in arbitrary units here. So the problem here is we cannot have any information about the true size of the extracellular vesicles. And then if we open the Rosetta calibration beads here, so those, so here you should see different, if I switch to histogram, we would be able to see different peaks. Okay, so each one of those peaks corresponds to a different size of polystyrene beads. Yeah, and on the left here, you can see some of the background noise from the cytosol. Yeah. So it's you can also see that with forward scatter and side scatter, you can see those peaks here, those different populations. Okay. So what do we do now? The next step is to select our Rosetta calibration beads FCS sample, and I can run my plugin on it. Okay, so I can select my sample, go to workspace, plugins, and then after installation of the plugin, you will have here a Rosetta calibration plugin to use. Okay, so I will select this one. You will need first to save also the workspace. I will save it as Rosetta demo in my desktop. And now the plugin starts calculating. So the first time, again, you would have to input the executable file of the Rosetta calibration software. But if you run it once, then you don't need to do this each time. So now it calculates the data points of the different sizes of polystyrene beads. And the next step here would be to open the Rosetta calibration software. Okay, so it's loading here. And now we have, you see here, we access the Rosetta calibration software. Yeah, so that was here my how the plugin works and calculates. So there are some options here that I would like to go through. So first of all, you have this calibration section here, which is the first step we need to do. And here you can input your flow cytometer settings. So as we said before, there are different cytometer supported that are supported by this software, and you can access this here. Okay. So by definition, using the $cytometer keyword, this will be automatically input correctly. But just in case that this was not done correctly, you can also access here its different kind of cytometer we have. And then you need to input the forward scatter. Yeah, so the channel for the forward scatter and for the side scatter. Yeah, and depending on the wavelength, you can input this one here as well, according to the manufacturer instruction. And finally, also the green fluorescence channel to input here. And then we're gonna press save here. And then we need to select the either a light scattering channel, and this can be either the forward scatter or side scatter. It is advised in most of the cases because it's more sensitive to use the side scatter for calibration. Yeah. So whenever I change here the channel, you will see that the projected data here changed. So when I use my side scatter, I observe here different peaks. So basically, this is a reversed histogram where we can see the scattering intensity of the side scatter and counts. Here would be probably my background noise, and those peaks are my different polystyrene beads. When I have like here visible peaks, I'm gonna next select and press calibrate. So basically what this will do is to project those peaks and those different peaks of polystyrene beads on a scattering versus diameter plot. Yeah, so this is what we said before. And through me-theory, it will connect those data points on this plot. Okay, so I select now simply calibrate. Okay, so now we see we have 4 different data points. So this corresponds to that peak. This is 200 nanometer peak here. And then we have 400 nanometer peak here. Yeah, so those are our data based on, so it's a standard curve that we have that we can use later on. And based on the polystyrene beads, so they have a known refractive index, you can see here using an index of 1.63, it calculated with me-theory this line. Yeah, so that we can use this to compare other samples. Yeah, so that's the first step. If you want, you can also change the magnification here. So if you want to display more larger diameter EVs, you can do that here. Next step is the following. We set the sample calculation parameters. What does this mean? Basically, this means that depending on what kind of sample we have, this might have a different refractive index. Yeah, so we need to input that in order to calculate this relationship between size, intensity of the scatter and diameter. This is preset here because in most of the cases, this software is used for extracellular vesicles. This is set according to the known and published refractive index of extracellular vesicles. So the me model that is used is core shell, basically because we have a different refractive index between the membrane and the inner part, the core of the extracellular vesicles. You can add the refractive index of the medium that the sample was collected, and all those are adjusted to reflect as accurate as it can be the refractive index of extracellular vesicles. So that is set here of those values. But if you have different kinds of samples or different different sizes of extracellular vesicles, you can contact also exometry to advise you which refractive index you should input in each case and how to modify those values. Okay, so now we will calculate the diameter to scattering intensity for our given sample that we input here. So I'll press calculate. And this now will project a line for our samples. And because we have a lower refractive index of the extracellular vesicles, this line will be like that. Okay, so now we can see where our samples would fall. So if we have a scattering intensity here of approximately 10 to the power of 5, we would have a diameter of approximately 300 nanometer EVs. Okay, so now the last step here is to press the return to flow job button. So basically this will return the calculation that we did based on the side scatter back to the sample. So I'll click here. Okay, so it's calculated. Now it is done. Initially you land here and you don't see that anything yet. What we need to do next is to drag and drop this node, the Rosetta calibration node, into your samples. Yeah, so you can just drag and drop that one here. Okay, so now what we have here is a new derived parameter, which is the diameter in nanometers based on the side scatter. And this is exactly what this plugin does. So now we have, if I open this plot here, I can switch to a histogram maybe, and then I will use my x-axis and I can use the diameter. So this is now a true standardized measurement of the diameter of the extracellular vesicles within my sample. Yeah, so this is the main function of the plugin. So we can proceed now, of course. When you study extracellular vesicles, you might be interested to identify different types and different phenotypes and what they express. So one way now is to set gates. So how you can proceed here is I could, for example, set a gate using that histogram for different sizes of EVs. So I can set a gate for my range of 400 to 600 nanometer EVs. And I can do another one, maybe 300 to 400. EVs. And then we can have 300 to 200. And so forth and so forth. I'll just make another gate here for 100 to 200. So, and you can continue and do this for all of the rest of the samples, or set different kinds of gates. And the next step, it really depends on what is going to be your workflow. Something useful that you could use is the layout editor here, where you can overlay all those different populations, because ultimately we want to see differences between those in different markers and so forth. So I can drag and drop those into my layout editor, and I can create maybe an overlay. So I can select the rest of the histograms and just overlay those into the same plot. Okay, so we have a legend here with the different size of EVs. And then I can switch this histogram to any different parameter. So now we see the diameter, but I can change the axis to any of the fluorescent parameter. Yeah, so I can use, for example, my fits here, fluorescence, and I can visualize the differences. Yeah. It helps here also, just in general, when you have overlaid histograms, you can always select right click on the plot, go to histograms, and change the visualization. Yeah, so you can have a half offset overlay, so we have 50% overlap between the peaks, and we already see some differences here concerning fits fluorescence. So we see that in the larger EVs we have more fluorescence here. And other kinds of visualization include stagger offsets. So you can use more like 3D visualization, and also the offset. Yeah, so a complete offset to compare those. Yeah. So so that's pretty much it. So this is what the plugin does and functions in order to detect the size of extracellular vesicles. I'll just check if there are any questions. I haven't seen any questions here. For any other question that you might have, you can contact me at ioannis.panetas@bt.com, or I also put here the exometry email, where if you have any questions about setting the refractive index of your particles, or your the samples you're interested, you can feel free to contact to get support and you know, define what the best refractive index for your sample would be. Okay. So thank you all very much. Are there any questions you have? You can type anything. We have a question: if the recording will be made available afterwards? Yes. I'll just show you where. If you go to our webpage, flojo.com, you can go into the Learn tab and Webinar. So this is where you subscribe for being here today. And at the top, at the bottom, there is this button, Recorded Webinars. Yeah, so if you select here, there is the list with all the recordings. Yeah, so this now should be this week or next week should appear first here, so you can rewatch it. Yeah. So. Are there any other questions? Okay. Okay, otherwise, thank you. Thank you all very much for joining, and see you soon in one of the next webinars. Bye-bye.